video, I'm going to be describing how we can graph rational functions. There's going to be two separate ways that we could do it. The first way is that we could use the transformation style of the function to talk about shifts and reflections. So if you know what the graph of the parent function, 1 over x, looks like, and you can sketch that out quickly enough, then if any of these transformations are applied, then you can stretch or shift that original graph and just come up with a quick sketch for what the new transformed graph may look like. For example, if we have the function negative 1 over x plus 2, well, we have two transformations occurring. The first being the negative part of our function. That's going to reflect the function across the y-axis. And that might be something a little different than you're used to. Usually, if we have a negative function, it reflects over the x-axis, but for rational functions, it acts a little bit differently, so be careful there. If we have a value that is added or subtracted right next to our input value, well, that's going to be a left or right shift, and you can think about it as being the opposite of what it looks like. So because it says x plus 2, it's really coming from the form of x minus negative 2, and so a negative 2 is going to be a left shift 2 units. So if it says x plus 2, just think the opposite, think left. This other example here, we still have two transformations, but they're both shifts. So because you have x minus 1 here, that would be a shift right 1 unit. And now we have this k variable over here. That's a vertical shift. Any constant being added or subtracted to your function is going to move up or down. And it's going to do exactly what it looks like. So if it says plus 3, you can interpret that as shifting up 3 spots. Unfortunately, not many rational functions come to us looking like they do in this transformed way. And so this isn't always the most helpful, but if you do see a function in that form, maybe you can just think or sketch it quickly enough. If not, if it looks different than that, then here are some tips for graphing. And we're going to work through, in the next couple examples, all of these steps here. So feel free to write those down or just look at them as we go over the next couple of examples here. All right, this first one is given to us in that transformed form. So if we know our basic reciprocal function that has this behavior happening, we're just going to shift or move these two graphs left, right, up, or down, or stretch them slightly. In this case, there is a stretch by a factor of 3, so our graphs are going to get stretched to the right, I guess, would be one way to describe it, or to the left. Just stretch slightly from their original arc. And then we're also going to shift right 2 units. So that asymptote that usually occurs right along the y-axis is going to get shifted to the right 2 spots, and the graphs are going to come with it. You can come up with some additional points or look at your data table to figure out how that stretch affects your points. But essentially, I mean, it's not going to be that much different. It's going to look pretty similar to its original graph, just moved to the right 2 spots. Just to practice these steps for our next example, let's figure out how we can do these things algebraically. Holes occur whenever we have common factors that get simplified or canceled. There are no common factors here, so there are no holes in our graph. Vertical asymptotes occur when we have zeros of the denominator. So if I plug a 2 in, I would get a 0 in my denominator, so that must mean that my vertical asymptote happens at x equals 2, so there we see that. This is not talking about a coordinate. This is the equation of a vertical line, so it's representing all points along that vertical line there. Horizontal asymptotes can occur 3 different ways. In this example, we see that the input has a degree of 1, which is higher than any degree that's on top, since there is no. And in that case, if the denominator has a higher degree than the numerator, then your horizontal asymptote will always happen at y equals 0, or the x-axis is a better way to maybe think about it. And so here we see that horizontal asymptote occurring. The graphs are going to approach that asymptote as they approach their end behavior. It is possible that graphs can cross or touch horizontal asymptotes, but not touch or cross vertical asymptotes. And so in this case, they aren't actually touching it, but in some cases they do. We may see that in the next example. To find a y-intercept, we know that our x values are 0. If we're on the y-axis, our x value is 0. So if we plug a 0 in for our inputs, the output will be our y-intercept. So plug a 0 in for x, we get negative 3/2 or negative 1.5. So right there we see that we cross the y-axis at that point. To find x-intercepts, we need our output to be 0 because our y values are 0 on the x-axis. And for rational functions, that means that you want to find zeros of the numerator, because if the numerator is 0, the whole function is 0. So we're just finding zeros of the numerator. In this case, we don't have any inputs, so we don't have any x-intercepts. While the horizontal asymptote did occur on the x-axis, that's not really the reason why we don't have x-intercepts. So be careful there, because we could have a horizontal asymptote occurring on the x-axis and still have an x-intercept because we're allowed to cross a horizontal asymptote. All right, having to figure out all that out, we know what our restrictions are on the domain now. So any of our inputs that are restricted, for example, x equals 2, that value is not going to occur in our domain. If we had any holes, that would also be a restriction, but we don't. So the only value we can't plug in is positive 2. So that means we can describe all inputs in our domain as being available except for 2. So in interval notation, we describe that as values that are less than 2 and values that are greater than 2. And our parenthesis right here means that we're not including the value of 2. I decided to try out an additional point just so I can make sure that the behavior of this graph was occurring the same, pretending that I didn't know that transformation was just my parent function shifted. So again, you can look at your data table for those, or you can plug inputs into your function to get outputs. I think if you have a graphing calculator, it's much easier to just look at your data table. All right, let's do one that is not in that transformed form. For example, this, in which case we got to follow these tips right here to try and get an idea of what the graph looks like. Always, when you're dealing with rational functions, try and factor and simplify the function as much as possible, and a lot of information is given from that factored form. For example, holes we could see occurring if we had common factors that were canceling. So unfortunately, again, we don't see any holes in this example. Vertical asymptotes, again, are zeros of the denominator. So in this case, we have 2 of them. We could have a 0 occurring at x equals 2 or negative 1. And we can sketch in those vertical asymptotes on those vertical lines. Horizontal asymptotes, again, we see the bottom degree being higher than the top degree. And so our horizontal asymptote is going to occur on the x-axis. You can sketch that in with a dashed line if you wish. Next up, let's find our intercepts. Those are the first points we want to plot. To find the y-intercept, we just set x equal to 0. So you could plug a 0 into all of these x's, but knowing that the numerator is going to be 0 means that the whole function is going to be 0. So we have a y-intercept at the origin, 0, 0. And so right there is a great example of what happens if we cross or touch a horizontal asymptote. We knew that the x-axis was a horizontal asymptote, and yet we still have points on the x-axis occurring. In fact, we have a y-intercept and an x-intercept. The reason why we have the x-intercept is for zeros of the numerator. So setting the numerator equal to 0, there's only one option there, it's 0. So the y-intercept and x-intercept are occurring at the same spot, crossing or touching that horizontal asymptote. Well, just plotting that point is not enough, so it would be helpful to come up with some additional points just to make sure we know what the behavior of the graph is doing on either side of our asymptotes. So on the right side, if I go just to the right of that vertical asymptote, I could check and see what point is on my graph. If I plug in 3, I could plug 3 into the function and evaluate it, although I could also just look at the data table and see my output for an input of 3. It's 0.75 or 3/4, so I could plot that point approximately, knowing now that my graph is going to follow the horizontal asymptote, I hope, but certainly follow the vertical asymptote as it approaches and goes up towards positive infinity. So it probably would have been a better idea to check one more point here and make sure that I wasn't crossing that horizontal asymptote. So I could check and plug in a value like 5 or 8 just to see if there was any point that I crossed. So again, just check your data table and see that you're not crossing the x-axis there, and you can better sketch in that behavior. Exact same thing on the left side now. So just to the left of my vertical asymptote, I'm going to plug in -2. If I have an input of -2, I see on my data table that I have an output of -1/2 or -0.5. And so this time I know my graph is below the x-axis and not above it. And it's going to be very similar to the behavior of this graph just down here. So it's going to approach my vertical asymptote and head towards negative infinity. And it's going to approach my horizontal asymptote. In this case, it's not going to cross, although it could have. And it's just going to follow that horizontal asymptote or x-axis as it moves left. So now we want to figure out why the middle graph looks like this. We knew our intercept there. So check just to the left of that. I would check maybe -0.5 or -1/2 and see an output of 0.4 or 2/5. So I know my graph is going to go up on the left side there as it approaches that asymptote. On the right side, just to make sure it doesn't keep going up on the right side, we'll plug in a value just to the right there, like +1. If I do that and look at my data table, I get an output of -0.5. And so I know that my graph, rather than going up as it approaches that asymptote, is going down as it approaches. And so in coming up with those additional points, I was better able to approximate the behavior of my graph. One last thing, we haven't talked about it yet, but there are these asymptotes that are unique. They're called slant or oblique asymptotes. They are asymptotes that follow a linear equation or a line, a diagonal line. Once again, graphs could cross or touch slant asymptotes, so they're not as strict as those vertical asymptotes. In order to find the equation of a slant asymptote, first check this rule. A slant asymptote will only exist if the degree of the numerator is exactly one more than the degree of the denominator. So we can see a couple examples of what that means. For example, here we have x squared on the top and just x to the first on the bottom. So because the numerator degree is one more than the denominators, a slant asymptote exists. And over here we can see another different example where we have x cubed on top, which is one more than x squared on the bottom. So another slant asymptote is going to exist. In order to find the equation of your slant asymptote, we're going to use either synthetic division or long division. Either way, we're going to divide. In this left case here, we see that we have just a basic binomial here on the bottom, and we can just think about its 0 and use synthetic division to divide. However, in this example on the right, we have a much more complicated polynomial there on the bottom, so long division form is going to be better to use because I can't easily just create a 0 of that numerator and divide it into it. So using synthetic division here, we can use the 0 of the denominator, use our coefficients of our function on top, and divide into it. We'll notice that we get a remainder. That'll often happen. We don't care about the remainder. What we do care about is just the linear function that is a result. And the reason why we will always get a linear function is because the difference in our degrees is only 1. So the difference in your quotient there will just be a linear term. So just using the linear variables, in this case we just have 1x plus 0, we could say, but we don't have to say that. So the equation of our slant asymptote is going to be y equals 1x. So just the most basic type of linear equation. So if you were to graph this rational function and graph this slant asymptote, you should see the behavior of this rational function following the slant asymptote as we go farther and farther away towards our end behavior. One more time, just an example of using long division. Whenever you're dividing, be careful if you're missing any terms as we go from leading degree down to the constant. You always want to put placeholders of 0 in those spots, otherwise your division doesn't quite work out as well as it should. So following along long division here, you can see an example. The result we get is 5x minus 15. Even though that remainder exists, we ignore it and just focus on the linear terms. So the equation of your slant asymptote is going to be y equals 5x minus 15. And again, you can graph this rational function and the slant asymptote and watch the behavior of the rational function follow the slant asymptote as it goes towards its end behavior. All right, so a few things to think about. Actually, a lot of things to think about as you graph rational functions. Try and practice these steps right here, and as you get more and more familiar, you'll eventually follow them as closely as you can and hopefully successfully graph rational functions.